Hello, students. Today we are going to talk about the puzzle of matter and actually why matter matters. So, chemistry is the science that investigates and explains matter. That's all the things that make up what you are. It's anything, matter is really anything that takes up space at all. For instance, it could be a bowling ball, the air you breathe, or stomach acid. Believe it or not, stomach acid is matter. And matter is made up of mass, and mass is the measure of the amount of matter that an object contains. If it is less massive, it has less matter. If it is more massive, it has more matter. And what are the units of mass? You guessed it, they are the gram, absolutely. And the properties of matter describe how that matter is going to behave and characteristics that we think of when we're talking about that matter. And these are also the changes that the matter could undergo. And we, as chemistry students, are going to study matter at the macroscopic level. That's what we can see, and that's based on the composition of the matter. But we're also going to think about the submicroscopic level of matter, or the atomic level, all the way down to a part that we can't even see with a microscope. And that's, if we can really understand that, we can predict what the macroscopic level is going to do, how to make things that we can see and we can use. To do that, to understand and explain things with the submicroscopic level, we use models. And a model of the atomic structure of a piece of matter must be able to explain and predict the observed behavior. And if you really understand chemistry well, this holds true. And you can see amazing things and implications of the submicroscopic level. For instance, with just three little atoms, carbon, oxygen, and hydrogen, in both sucrose and in aspirin, we have very different behaviors. Aspirin we take in order to stop prostaglandins from being made so that we don't have fever and so that we don't have pain. And sucrose we take in as a source of energy. We really need it to drive cellular respiration, so we have ATP and we can do things in our cell. Just three little atoms can be arranged in different ways to do very, very different things. So let's classify matter. First, let's talk about a substance. It's got exactly the same fixed composition and materials. It's pure, meaning every single bit of it is exactly the same substance. So it could be pure sugar, pure water. That is a substance. And then we also have a mixture, and that's a combination of two or more substances in which the basic identity of each substance is not changed. But that's at the basic level. You can change them relative to each other, each of these substances within the mixture. Most things that you see are going to be mixtures because it's very difficult to obtain the pure substance. But we can use physical processes in order to separate out the substances within the mixture. But since we mostly see mixtures, we're going to talk about the different types of mixtures first. And pure substances would be like oxygen or like water, pure H2O, no impurities at all, very difficult to get, but that is a pure substance. So let's talk about mixtures. A heterogeneous mixture does not have a uniform composition, and its individual substances remain distinct. So the substances are always going to stay apart, and if you wait long enough, even if you mix them up, they will separate out again. A great example is eggs. If you crack an egg, you put it in a glass, you will notice that it will separate out. Even if you scrambled that all up before baking it, of course, that's a chemical change, which we'll get to later. But if you don't bake it, you just leave it in its glass, it will separate back out. And you'll see that it's nice and separated here in the picture. And remember, homo, H-O-M-O, means same. If you're a homosexual, you have a preference for the same sex. So a homogeneous is all the same, all mixed up. Another name for that is a solution, and it's always uniform and the same throughout the mixture. An example would be salt water after it's been dissolved. You can't really see the salt, it all looks clear. A special type of solution is an alloy, or a solid solution that has different metals and sometimes non-metallic substances. So when you hear things like sterling silver, that's actually silver and copper. Steel is iron and carbon. And bronze is copper, tin, and zinc, like our friend Einstein here. So an alloy is just a solution made of metals, and they may also have non-metallic substances like carbon in them. So when you have a mixture, you're going to have a solute and a solvent. A solute is the substance that gets dissolved. And these get really confusing, so I'm going to give you some ways to remember. Remember, solute sounds like cute. It could be like a cute little guy. And there's always going to be less of the solute than the solvent. Otherwise, the solute can't dissolve in the solvent. So remember, cute, little, or like sugar, cute. And the solvent is the substance that dissolves the solute. So always remember, the water is the universal solvent. We have the two V's, universal solvent, and that's water. And when the solvent is water, the solution is called an aqueous solution. So remember, solute, oh, we've got these cute little sugar cubes, solute, cute. And there are two types of pure substances. So mixtures can either be heterogeneous, that's dirt, blood, milk, or homogeneous, soda, gasoline, air. They all look the same throughout. But you can use physical changes, we'll talk about these later, separation techniques to get the mixtures down to their pure substances. And those pure substances can be either elements or they can be compounds. Elements are oxygen, gold, iron. You're going to see these on the periodic table. And compounds are salt, baking soda, and sugar. So an element is as pure can get. Pure hydrogen, pure helium, pure carbon. That's an element. And thus far, we have 118. We just got a new one. But only 90 occur naturally on Earth. The rest are made in a lab. And the periodic table, you can thank Mendeleev for this thing. It's super useful. We'll talk a lot about it throughout the year. You've seen it before. Now we're really going to hammer home how to use it, why it's important. And it uses chemical symbols that are understood universally, provided the alien or person has seen this before. But this is used all around the world to really explain elements so that different people can communicate different things. Elements. And a compound is a chemical combination of two or more different elements joined together in a fixed proportion. Many, many things that you've talked about before are compounds. Water, H2O, ammonia for cleaning, NH3, carbon dioxide, CO2. You may have heard of climate change. This is highly related to carbon dioxide. And then hydrogen peroxide. You may have used it on cuts. There's a big debate on whether it's useful or not. However, a little known fact, hydrogen peroxide is useful in removing excess earwax. Now, don't try that at home. There is a safe way to do that, but I've used it and it has worked. So hydrogen peroxide, guys, is just H2O2. So similar to water, it's just one extra oxygen, but just the differences make it either deadly to bacteria or very, very helpful for all organisms. So that's how we organize matter. I hope this was very helpful, and I will see you very soon.